Welcome, educators. Today we're exploring an engaging and hands-on activity perfect for your Calculus 1 class. This optimization project will not only enhance your students' understanding of calculus concepts, but also provide a practical application they'll remember. Let's dive into why this is the perfect in-class activity for your students. First, let's talk about the materials. Everything you need is simple and readily available. You'll need some letter-sized paper, which is 8.5 inches by 11 inches. It's easily accessible and cost-effective. If you really can't find letter-sized paper, then any size paper will really do, but you'll just need to use your ruler to get those dimensions. You'll then need scratch paper, which is essential for performing and jotting down calculations. A scientific calculator, which will be used for basic calculations and, of course, advanced complicated calculations during the activity, because if they were really basic calculations, you shouldn't really need to use a calculator for that, and you can just do that by hand. And really, a scientific calculator, I want to emphasize scientific, because that is the most of a calculator that you will be allowed to use. Because if you get a graphing calculator, students then can find extrema using that without calculus, and that really defeats the whole purpose of the activity, because you want to ensure that students manually find the extrema using calculus. You'll then need a ruler for precise measurements. This is really crucial for accuracy in this activity. A writing utensil, I don't know why I even need to mention that, but it's really just for your calculations and, of course, for marking measurements when you want to actually cut the paper. Scissors, of course, to cut the paper and create the box. And, talking more about this activity here, it's more than just a theoretical exercise. It's really a practical application of calculus principles, as students will use their knowledge of optimization to create the largest possible open-top box from a single sheet of paper. So here's like a step-by-step look at how this activity, is supposed to be done. So they're first going to want to find the actual volume equation. So I'm just going to sort of give you a head start here, right? Of course, if you're a calculus teacher, you should know what I'm sort of talking about. They'll need to cut out x by x squares, right? So these are not really good looking squares, but x by x squares. And they need to find the largest x value in order to make the largest box. So that largest box implies volume. Volume is length times width times height, right? This is 11 inches. This is 8.5 inches. Right, so then V equals to 11 minus 2x times 8.5 minus 2x times x. Okay, so this is what they really need to find. They then need to talk about need to figure out the domain. Like this is super important, because it makes them understand that this in general, this is a polynomial. This is a polynomial function in the context of just pure mathematics, but this is a real-world application. So x, we know, cannot, we can't have 0 as a volume. We can't have a negative volume. And using those sort of criteria here, because, that's sort of common sense. We want to actually have a box, so volume has to be greater than 0, and the box cannot have a negative volume, because that's just impossible. So then it makes students sort of think about well, how can I find the interval or the values of which x can be? So that's what they should immediately do after finding this, because you shouldn't skip to finding the derivative and doing tests and all that, because it will potentially lead you to the wrong answer. And again, this can be a trial and error process. If you grade students on this activity, I feel like it should be solely off of completion and like showing their work, because if they don't get the domain automatically, they could just see here like, oh, if I get some negative sort of x value, how will I cut a negative square with a negative side length? So again, it's a trial and error process, which is also good. So that's, again, I wouldn't recommend grading it off of accuracy unless you really want, like, unless it's like an actual test question, like you don't do this as a hands-on activity, which is more common. Like if you see this type of thing, it's more of an actual test question where they give you a paper with the dimensions and they say, they even give you this sort of picture here and they say, find the maximum volume, or find the, sorry, not the maximum volume, find the area of the squares, or like the amount, or the what x has to be to create the largest volume. Okay, so once they find x, you know, doing the calculus, checking critical numbers, etc., you want students to actually cut the squares, right? You want them to create the box now. So they find x, they find what x equals to, then they cut the squares according to that, then they fold it. You know, you don't necessarily have to tape it, but if you want the actual full box, you can tape the sides, so then you can have your actual completed box. So that's really it in terms of doing the actual activity. I would say that, you know, some more benefits of this is that it's hands-on learning. It makes abstract concepts, you know, easy to grasp. Abstract concepts easy to grasp. You know, engagement. These are interactive, so it helps students maintain interest and excitement. Collaboration, you know, having students work with their peers. It encourages teamwork and communication. In terms of, for you guys, teachers, it's educators, it's, you know, preparation. It's super easy. They're simple materials, inexpensive stuff that you can find around the classroom. The purpose or the objective is really clear. It really ties into the curriculum goals for calculus and optimization. You're not wasting time by doing this. You are genuinely, you know, in fact, you're even going outside of the curriculum in a way, in a good way. Like, it helps students just sort of appreciate, they get motivated, like, oh, I can do this with calculus. What more can I do with calculus? And it also just finds a way of like assessing the students, not necessarily off of accuracy, but maybe how they're doing. Like you can check on students, say like, hey, did you find your critical numbers yet? Or did you find your domain? Or did you, you know, it's very nice to see, you know, it can sort of serve as like a progress check in a way, like how is the student doing in this hands-on activity? So really, I think that incorporating this optimization activity into your Calculus 1 curriculum is a fantastic way to enhance learning and just bring practical application into the classroom. So try it out. Watch your students' understanding and enthusiasm for calculus grow. Thanks for watching, and happy teaching.